In this video, we're going to look at finding the average value for a function where our computation of the average value will involve an integration technique. So here we want to find the average value of the function e to the sine x cosine x on the interval from 0 to pi over 2. So we know we need to apply our average value formula. So we'll have 1 over b minus a, so in this case that's pi over 2 minus 0, times the integral from 0 to pi over 2 of our function e to the sine x cosine x dx. So looking at doing this integration, we see that the integration technique that we're going to need is u substitution. And so this is a very common integration technique that we'll see in a lot of different problems. Notice that I need to take u to be sine x, so that my du is the derivative of sine x, which is cosine x dx. So I see I'm going to have 1 divided by pi over 2, which will be 2 over pi, times the integral of e to the u du. And now I have to think about remembering to change my limits. So I need to make sure I get u limits. Okay. So notice that when x is 0, u will be sine of 0, which is still 0. And when x is pi over 2, u will be sine of pi over 2, which is equal to 1. So my new limits will be from 0 to 1. So now everything's in terms of u, and we can just go ahead and take the antiderivative and plug in our u limits. So we'll have 2 over pi e to the u evaluated from 0 to 1. So these are u limits. This antiderivative is in terms of u, so I never have to go back to being in terms of x. So I have 2 over pi e to the 1 minus e to the 0, or 2 over pi times e minus 1. So that's our average value for this function. Okay, so we'll notice that in several of the average value computation problems that we'll be doing, we'll also be practicing our integration techniques along the way. But let's just finish off this problem by looking at the geometric interpretation and maybe how we could interpret this average value if it was in the context of some kind of application like velocity. So first we'll look at the geometric interpretation here. So we have this curve where this is our function, f of x equals e to the sine x cosine x, and this horizontal line here is my average value, which was 2 over pi times e minus 1. So again, this is f average, and this is my function f of x. And so we can see this is showing how the area under my curve from 0 to pi over 2 of f of x dx is equal to the area of the rectangle computed by looking at this value of f average times the overlapping time of pi over 2, or excuse me, the overlapping interval here of pi over 2 minus 0. So we know that these two things are equal, these two gray areas are equal, and we know we can see that by also seeing how if I cut off this part here, it would be used to fill in these parts, these parts of the rectangle. Okay, so we can see how geometrically each of those gray areas were the same. So just to give you a little bit more ways to think about this, maybe in the context of a familiar application like velocity, say f of x was the velocity of an object in meters per second. Okay, then we know that the area under a velocity curve, okay, then the integral from 0 to pi over 2 of f of x dx would represent what? Well, when we integrate velocity, we would get back our position function or distance. So this would actually be equal to the total distance traveled over the interval. Okay, and from our work that we did above, that total distance traveled would actually be equal to e minus 1 meters if we're giving our distance units of meters in this example. And this would be because f of x is actually positive, that we're having a total distance traveled in the case of this example. Okay, so the area under a velocity curve will represent distance traveled. Now I can look at this rectangular piece then as representing what? So this rectangular piece is then f average times this pi minus 1, excuse me, pi over 2 minus 0. Okay, where that f average, in the case that f is velocity, would actually be average velocity. So this is my average velocity here, which would be 2 over pi e minus 1 meters per second times pi over 2 seconds. So we can see how this would be giving us that e minus 1 meters. Okay, so you can see in an interpretation here how this distance, okay, we can think about this first one as representing distance, and this second one is representing like rate times time. So we know distance equals rate times time. So that gives you another way to sort of think about this interpretation in the context of an application. Please let me know if you have any questions on anything in this section.